right, so let's look at number 4 to start. Number 4 was a graph of a derivative function. So you had to use that table I gave you to go backwards and figure out key pieces of information about the original function. So in part A, it asks you to find the relative max. In order to be a max, the derivative has to change from positive to negative. So in order to get your 2 points, you had to identify both the -2 and justify that the derivative went from positive to negative. So that'll get you 2 points in A. In part B, it says the graph of f is concave down and decreasing when, well, f is concave down and decreasing when f prime is both decreasing and negative. So your reasoning is decreasing and negative, and then your intervals were -2 to -1 as well as 1 to 3. If you only had one interval, you could not earn the interval points. So you had to have both intervals to earn that point, and you had to have a reason, and your reason had to have f prime is decreasing and negative. You had to make sure you specified f prime. Yes? So if f double prime is negative, so how did you, I guess where they're going to maybe catch you, it would be, how do you know f double prime is negative? Yeah, you would have to have shown that somehow. Does that make sense? Because what they're stating is identical to what you see in the given graph. It's not that it's wrong. You would just have to say why you know f double prime is negative, and your reasoning is because f prime is decreasing. So you almost have to put that anyways. Okay, part C. The graph of f has a point of inflection at -1 and 3 because f prime changes from decreasing to increasing and or increasing to decreasing. So you could make two statements, or you could list both points and then say, you know, increase to decrease, decrease to increase. Yep. I'm trying to determine if you can have a horizontal tangent that's not a POI. Yes, you can. So that wouldn't work because you could have a horizontal tangent. This is not going to be drawn wonderfully, but you could have like a graph that stays decreasing, and then that could be a horizontal tangent in there, therefore not a POI. And then part D. Part D was an initial value problem. So you were looking for your net change. So you were given an initial point and you wanted to find the change from that point to the next point. So if you were told it had 3 to start and then you go from 3 to 1 to 4, you see that it's gone backwards -9. And then at -2, you would do vice versa. Start with that 3, go from 1 to -2, take your area backwards, and you get 12. Okay, I had to skip 5 because we're going to look more about that stuff later this week. And then I had you go over to number 6 because we've been doing a lot of calculator, rate in, rate outs, and that's kind of what number 6 is. So number 6 came from the 2015 exam. For part A, you wanted to just find the area under the curve for that function. So you needed your integral, which was 0 to 8 r of t dt. That earned you 1 point. And then you needed your answer with 3 decimals. That earned you your second point. So again, we're looking to get 5 points per question. If you can average about 5 points per question, that gets you a 3 or 4 on the AP exam. If you're averaging 6 to 8 points, you're going to fly high and get your 5. Okay, part B is the amount of water in the pipe increasing or decreasing at time t equals 3. So in order to determine if it's increasing or decreasing, I needed to know what the value of the water was. So that was R of 3 minus D of 3, which is negative. Since it's negative and less than 0, that would mean that R of 3 is less than D of 3. Therefore, it is decreasing at time t equals 3. So you could have just compared these two numbers and said R of 3 was less than D of 3. That earned you your point. You could have set them equal to each other and gotten that answer. That would have earned you your point. But you needed to have some comparison of R3 and D3. You needed to have either both of their values or their final value, and then your reasoning. So I feel like we've seen it and seen it and seen it. Part C. Part C is that EVT idea where you are checking your endpoints, you're checking the critical point, and you're justifying why you have a min or a max. You can almost guarantee that you need to do this at some point on your AP exam. So you'll be setting the derivatives equal to 0. In this case, the quote-unquote derivative was the given function because R of t was given to you as a rate. A rate represents that idea of the first derivative. So that's what makes this one a little bit tricky. They're making sure you understand that R and D represent that rate, which kind of represents that derivative. Questions, comments, anything? How do we feel so far? Are we doing pretty good? Better than we've done in the past? Better than we thought our mock exam was? Are we getting those 5 out of 9s we're hoping for? Okay, and then part D. You have your net change plus your change in position equal to a value. This represents overflow because the rate in is going to be greater than the rate out. You could have subtracted the 30 and had 0w r of t minus dt equal to 20 also. That was an alternative answer if you had the integral equal to 20 because you subtracted 30 from it. If you just had the integral, you still earned 1 point. So if you just had 0 to w of r of t minus d of t dt, you still got a point. Okay? Questions, comments, concerns, anything that wasn't covered? Because again, that's just the scoring rubric. That doesn't always necessarily take you through everything in detail. Let's look or check over the 4 multiple choice questions from the IVT, EVT, MVT packet. Okay, number 1 was B. It's B because this is a special case of MVT. It's the application of rules that requires you to say that f of A must equal f of B. A would be true by MVT, and C are true by EVT, and E is the definition of the derivative. So B is the only one that works because it's the only one that's false. Number 2, the correct answer is D. This did not come from a past AP exam. It was created to represent an AP question. So you can see slope of the tangent equals slope of the secant, aka application of MVT. Slope of the tan equals slope of the secant. Solve for that value and you get plus or minus the square root of 5. It's only the positive because of the interval that was given. Okay, number 3. I'll give you a second. The correct answer was A. That one's a little easier to read than it is for me to read to you. And number 4. Okay? So that's sort of a wrap-up summary of all of our theorems. It went through each of the main ideas. Again, IVT does not involve a derivative. So if you're thinking of your theorems, IVT does not involve a derivative. So if you're having trouble choosing, IVT will not have a derivative. MVT will involve a slope. So you'll usually see the word slope or rate of change. EVT is going to ask you to find an extrema. It's either going to be an absolute, going to be an absolute max or an absolute min. So what we're going to do today is change our focus away from those theorems and back to our favorite theorem, which is the fundamental theorem of calculus. The fundamental theorem of calculus is going to involve being able to understand the relationship between an integral and a derivative, as well as an initial condition and its closing points. So what I want to do is start with you on our fundamental theorem packet. So we have the integral of 2e to the x over 2 dx. So anytime you have a constant, it comes out in front. So this is equivalent to 2 the integral of e to the x over 2 dx. So this is a u sub problem because you can't have x over 2 in there because that's like a function to a function. So I would say u equals x over 2. du equals 1/2 dx. I don't have a 1/2 in my problem, so I'm going to multiply both sides by 2. So this is going to end up becoming 4 e to the u du. And then antiderivative of e to the u is e to the u. So we get 4e to the x over 2. There are no bounds. So if there are no bounds, we must add back our constant of integration. So we can see that the correct answer is A. Okay? Number 2. In number 2, we have a piecewise function. So it says let g be the piecewise function defined by g of x equals what is the integral from -1 to 3 of g of x dx. So if you are going to cross over breaking points, then you have to write your integral as every breaking point. So to find the integral from -1 to 3, I have to consider the integral from -1 to 1, because that's a breaking point. So from -1 to 1, that's x values less than 1, so I'm integrating a function 2x. And then I have to consider the integral from 1 to 3 for x values greater than 1. So that's x squared. And now at this point, I'm going to antiderive. So antiderivative of 2x would become 2x squared over 2. So the 2's are going to cancel. Once you take your antiderivative, the dx goes away, but no sooner. So then I plug in my bounds of 1 and -1. And then I'm going to add to that the antiderivative of x squared, which is 1/3 x cubed, from 3 to 1. And then at this point, I'm going to plug in my bounds. So 1 goes in for x squared minus -1 squared plus 3 cubed over 3 minus 1 cubed over 3. So here, -1 squared would become +1. But then 1 minus 1 becomes 0. 3 cubed is 27. 27 divided by 3 is 9. So you get 9 minus 1/3. And in terms of these problems here, they're all in fractions. So 9 is really the same as 27/3. So we get 26/3. Which is C. Okay. Number 3. After a game, people leave a stadium at a rate. So again, we have a rate. So that means R of t is like a derivative. People per minute where t is measured in time. Selected values of R of t are shown in the table above. Use a left Riemann sum with 3 subintervals. So it's a left, it's 3, to approximate the number of people who leave the stadium during the first 15 minutes after the game. So 3 subintervals. Here's interval 1, interval 2, interval 3. It's a left subinterval. So that means I'm going to pick the values in the left, or on the left side. So that means I'm not including the 15 and the 50 in my data points. So the width from here to here is 3. The width from here to here is 2. And the width from here to there is 10. So remember, it's width times height. So it would be 3 times 300 plus 2 times 300 plus 10 times 100. So that's 900, 600, and 1,000. So that's 1,900. 1,900 plus 600 more would give you B, 2,500. And again, I know that the units are right because this 300 would be people per minute, and then the 3 would be minutes. So you would have minutes times people per minute. So your minutes would cancel, and that would leave you with people. Number 4. The graph of g prime, the derivative of g, is shown above. it is composed of a semicircle and a line segment. Determine g of 7 given g of 0 equals 2 pi. So this is a FTC where you have an initial condition and then you're trying to use the area to find the remaining point. So if I am looking for g of 7, then I need the integral from 0 to 7 of g prime x dx and we have to recall that that equals g of 7 minus g of 0. So that's your fundamental theorem. This is what we are looking for. So I'm going to use that idea to say that g of 7 equals g of 0 plus the integral from 0 to 7 of g prime x dx. G of 0 was given to me, that's 2 pi. Zero to 4 is going to be a quarter of a circle of radius 4. So area of a circle is pi r squared. The radius of this circle is 4. And we are only looking at a fourth of it. So the area would be 1/4 pi 4 squared. So one of your 4's would cancel, and we would get 4 pi. And then this area from here to there represents a triangle. So it represents a triangle of base 1, 2, 3. And then height of -4. So area of a triangle is 1/2 base times height, or -6. So we have 2 pi plus 4 pi, which gives me 6 pi. And then my area of the triangle below is -6. So D, or 6 pi minus 6. We're going to skip 5 because 5 is an arctan, because you could technically factor that. And it would be a u squared plus 1 on the bottom. But like I said, don't have to worry about that. Okay, number 6, however, is not an arctan. So in number 6, we have the derivative of the integral. So this is the fundamental theorem where if you take the derivative of the integral, you just plug in your bounds. Now this one's a little bit different because the bound is in the denominator. If you want the bound to be in the numerator, you could multiply by a -1. So this equivalently would be the same as negative d dx of 3 to x squared. I would pull out that 1/2 sine t dt. Remember that when you plug in a bound that is something other than x, you have to also multiply by the derivative of it. So this becomes -1/2 sine x squared times 2x. So the 1/2 and the 2 cancel, and we get -x sine x squared, which is answer choice A. And again, if you didn't flip it and make it negative like I did, then you probably picked answer choice B, or not B, sorry, rather C. But the idea is that you had to take into account that truly, since that 3 value is a constant, when you take the derivative and the integral of a constant, it zeroes out. So that's why it ends up becoming A, and why I like to flip it and put the variable up top. Okay, number 7. You could think of this as using the properties of limits and properties of integrals, which says you can break all of them up. So the 2 comes out in front. We substitute 3, 5 from above with 6. So I get 2 times 6 minus, now up here you'll notice again this goes 5 to 3 and mine goes 3 to 5. So to flip it, you make it negative. So instead of being a positive 4 in substitution, it's going to be a -4. Which gives you 16. Take a minute, read number 8. So it says average value. So the minute I see average value, I am thinking I am dividing. I am finding an average. Here's my A, here's my B. So the average value of the function is 4. So it actually gave me my value. What is the area of the region bounded by f of x? The line x equals 3, the x-axis, and the y-axis. So I'm told that the average value of the function is 4. I'm told that we're bounded to quadrant 1. We have the line x equals 3. Totally started to draw in y equals 3. So there's my line x equals 3. Here's my x-axis, here's my y-axis, and here's my curve. I don't really care what my curve looks like. It could have been linear, it could have been quadratic, it could be square rooty, it doesn't matter. What we're told is that shaded area is 4 when you go from 1 to 3 minus 0 of 0 to 3 of f of x dx. That's what that says, because it's the average value, so that's 1 to 3, 0 to 3 of f of x dx. What is the area of the region bounded? Well, I need to get rid of this 1/3, so you multiply both sides, and you get 12 equals the integral from 0 to 3 of f of x dx. What does an integral represent? An integral represents area under the curve. So if the integral is equal to 12, the area of the region bounded is 12. Does that make sense? You can see how we work backwards to that. Okay, and then it says select the equivalent expression. So this is setting up a u sub, but not solving a u sub. So you always make the u sub the stuff inside the complicated fraction. So in this case, u would equal x plus 1. du would equal dx. But then we run into the problem that we have that extra x. So that's the case where I have to rearrange and solve for x over here and say that x is actually equivalent to u minus 1. So if u is equal to x plus 1, x is equal to u minus 1. So then I'm going to replace this x with u minus 1. I'm going to replace the x plus 1 with u and dx with du. So the equivalent expression would look like that. Which is answer choice D. Okay, and then number 10, while studying, the number of questions for just getting correct increases at a rate modeled by Q of t, where t is time in hours and Q of t is measured in questions correct per hour. So again, Q of t is representative of a rate. Which expression would give the number of questions Verge got correct in 3 hours of studying? So if Q of t represents a rate of correct questions per hour, do I want to integrate or derive to get questions? Yeah, I want to integrate. So goodbye C and D. Now you got a 50-50 shot. Am I integrating the rate of the rate or integrating the initial rate given? Yep. Okay, so that timing's pretty good. We finished through the multiple choice. Take your break with the rest of the world. Come back when that next bell rings. And we'll do some FRQing. Two particles move along the x-axis from 0 to 8. The position of particle P is given by this function, while the velocity of particle Q is given by that function. This is a non-calculator question. Particle Q is at position x equals 5 at time t equals 0. So that's an initial condition. When is particle P moving to the left? So we need to take particle P's equation and find its derivative. So a particle is moving to the left when the derivative is negative. So I'm going to derive x of P. So that's 1 over t squared minus 2t plus 10 times derivative of that, which is 2t minus 2. So I can factor out a 2 from the top, leaving t minus 1. And then for the bottom, factors of 10 that are negative 2 apart. So maybe you try to work through and factor that. So you would need both to be positive or both to be negative. And since the middle term's negative, they would both need to be negative. So there are no two negative numbers that are going to multiply to 10 and add to 2. So your denominator is going to be unfactorable. So again, it's that whole idea of last number, middle number, and two numbers that multiply to the top and add to the bottom. And again, in this case, since the bottom is negative and top positive, they had to both be negative. So, going through your factors of 10 real quick, it's 1 and 10, doesn't work. 5 and 2, doesn't work. So now in order to find when the particle is moving left, I need to find or compare the zeros of that. So 1 0 would occur at t equals 1. And if you think about your denominator, that's a quadratic. It's not factorable. And it's got this plus 10 y-intercept. It's positive. So this quadratic is going to be a quadratic that's shifted up and doesn't cross the x-axis. Therefore, it is positive always. So there are going to be no points at which this is negative. That also should make sense because the domain of a natural log is all positives. So the denominator is always positive. Our only point of concern is 1. So we're going to compare between 0 and 1 and 1 and 8. So plugging in 0.5. So 0.5 minus 1 is negative 0.5. Negative 0.5 times 2 is negative. We just said the denominator is always positive. So it makes it negative from 0 to 1. Plugging in 3. 3 minus 1 is 2. Positive, 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 positive. So that's positive. So when is the particle moving to the left? The particle is moving to the left when x prime of p t is less than 0, which is 0 to 1. Okay, from 0 to 8, find all times t during which the two particles travel in the same direction. So we already know the direction of travel for P. We just found that. Now we need to find the direction of travel for Q. So the derivative of Q, sorry, they actually gave me the derivative of Q. I just went back and reread because this is the position, this is the velocity. So therefore, that is my derivative. So factors of 15 that sum to negative 8. Again, this is positive, middle's negative, so both are negative. So we get 5 and 3. So I need to know what's happening between 0, 3, 3, 5, and 5, 8. So if you plug in 1, 1 minus 5 is negative, 1 minus 3 is negative, and negative times a negative is a positive. From 3 to 5, if you plug in 4, 4 minus 5 is negative, 4 minus 3 is positive, so that's negative. Plug in 6, positive, positive, positive. So this is Q, here's P. So if we want to know when they're going in the same direction, I need to know when their signs are the same. So they have the same sign from 1 to 3. And then 5 to 8. So it says final times during which the two particles travel in the same direction. So the particles travel in the same direction at 1 to 3 and 5 to 8. And if you had to justify, it would be because they have the same sign on velocity. So part C of that same question says find the acceleration of particle Q. So again, they gave you velocity. So acceleration of Q is the derivative of the velocity which was given to you. So you get 2t minus 8. So then we want to find that value at 2. So you get negative 4. And then it says, is the speed of the particle Q increasing, decreasing, or neither at t equals 2? Well, in order to talk about speed, you need to compare velocity and acceleration. So I need to also know v of q of 2. So you get 3. So since acceleration is negative and velocity is positive, then they are going in opposite signs. So then that particle is decreasing its speed. Your justification or your reasoning would be at time t equals 2, the speed of the particle q is decreasing because velocity and acceleration have opposite signs. Part D, find the position of particle q at the first time it changes direction. So you go back to part B and you say, okay, particle Q was forward from 0 to 3. So the first time it changed direction was at 3 seconds. So I want to find the position of Q at 3 seconds. So I want the position of function Q at 3 seconds. That's going to equal the position of function Q at 0, because they gave me that initial. It was given to you that particle Q's position at time 0 was 5. Plus, I have to integrate its velocity from the initial condition to where we're ending. So P of Q of 0 is 5. We're going to anti-derive the velocity. So you integrate and then evaluate from bounds. What's nice is since you're at 0, you can just subtract 0 away. So you get 5 plus 9 minus 36 plus 45. So again, 5 and 9 is 14. 14 and 45 gives you 59. And then 59 minus 36. And again, they actually accept this as a numerical answer. But 59 minus 36 is 23. So the position of particle Q at time 3 is 23. Okay, so here's what we're going to do. I'm going to give you another FRQ to try on your own. After you do that, I'm going to pass back yesterday's FRQs. So once again, clear desks, no calculators. I'm going to give you your 15 minutes to try particle motion just like we did yesterday. Okay, you may begin. I'll give you your 2-minute warning. Oh, I'm sorry, Caitlin.